Hello everyone, welcome to this video presentation of the LSA encryption algorithm. Um, I'm doing a video because we should have presented this algorithm at the American Mathematical Society meeting at Tufts University in Massachusetts on March 22nd. Unfortunately, because of the spreading of the coronavirus, the meeting has been cancelled, obviously. So if you are curious to know how this algorithm works, I'm going to explain it here. Well, I'm going to assume a very little knowledge of yours in number theory and group theory, very basic, just about the basic concept of group, the basic properties, closures especially, and I'm going to state and explain a little the theorems that are going to be used for the encryption. However, I'm not going to give any proofs, since especially the proof of Gauss's generalizations of Wilson's theorem is very long, so the video will be too long and it will take away from the procedure of the algorithm itself. Alright, so without further ado, let's dive into the math. I would like, before starting with the Gauss's generalization, then how about I start by stating Wilson's theorem. So, sorry, I apologize if the audio won't be at a level of a regular YouTube. This is the first video I'm doing, and I'm just speaking through my headphones, so I hope everything will be clear. Alright, let's start with Wilson's theorem. It says that let P be a prime number then it's true that P minus 1 factorial is congruent to -1 mod P. Alright, to be a little more clear, if we want to unfold these terms, we have the 1 times 2 times 3 times all the way to P minus 1 is congruent to -1 mod P. This is a very powerful and beautiful theorem, one of my favorites, especially the way we can prove it. I think is a very clever, unusual way. You can, like, is available everywhere if you're curious. This states that no matter what P is, if you multiply all the numbers, all the integers less than P, then you generate an element that is congruent to -1 mod P, so basically P minus 1. So, I see it sometimes as assume like we're playing, we have to play in a symphony, and there's an orchestra, and P is the size of the orchestra. This theorem says that no matter the size of the orchestra, it can be very small, it can be huge, when all the instruments are tuning, are playing the same note, they all are, the result is always the same. It's always -1, it's always the same, I don't know, chord or the same melody, I don't know. But this is Wilson's theorem. Now, Gauss's generalization of this applies the same concept not only when P is prime, but with every integer in the following way. So let's, sorry about that. Okay, let's try Gauss's generalizations or Wilson's theorem. It says that um, let's first we need a we need a group first. We need a set of elements equipped with an operation. So let's call this group UN. This is the notation I've learned. I know that some people write this group this way, right? I think this is a very hard notation for the explanation of this theorem. Would take longer time, so I'm going to use my notation, and this is the group of all the integers less than n that are co-prime with n. So the group of all the elements we call A sub 1, A sub 2, A sub 3, all the way to A sub phi of n, equipped with multiplication modulo n. First note, why A sub phi of n? Phi of n is a phi function, is Euler's torsion function, and the function represents the numbers of the element, the numbers of integers that are coprime with n less than n. So obviously there are phi of n numbers of element in this group over here. To be more precise, we have that AI is less than n, and that GCD between A sub I, so between all the elements n, is equal to 1, and we have obviously that 1 is less than or equal than I is less than or equal than phi of n. Okay, so this is our group. So Gauss's generalization, so Wilson's theorem says that let P be an odd prime also let call it T be a positive integer, or let's write it this way, it's probably better. T be a positive integer, then in UN, so in this group of integers less than n coprime with n equipped with multiplication modulo n, we have that the product of all the elements equal 1 to phi of n is equal to 0 if n equal 1, negative 1 if n equal 4, p to the power t, or 2 times p to the power t, 1 otherwise. How amazing this is. This theorem is Wilson's theorem on steroids, basically, because it says you don't need p to be prime. You don't need you don't need n to be a prime number. It works with all the integers. You can do it with all the integers as long as you work with the integers less than that one and comprime with that one. Note that Wilson's theorem is in fact a specific case of that, and as the case where p is a prime number and t is equal 1. In fact, it says that if this is true, then phi of n is going to be equal to phi of p, and all the elements that are coprime with p are all the integers up to p. Okay, let me make a few examples. Let me show you, for instance, if we work with U9, for instance. So everything is going to be more clear. So U9 is, remember, the integers less than 9 coprime with 9. So 1, 2, 4, 5, 7, and 8. Okay. Then note that 1 times 2 times 4 times 5 times 7 times 8 is equal to 2240, which is indeed congruent to 8 mod 9, which is the same thing as saying which is congruent to -1 mod 9, since the element whose n minus 1 is obviously congruent to -1 mod n. If instead we were to work with another group, why this is work? Because 9 is in this form. In fact, 9 is equal to 3 square, which is an odd prime number raised to a positive integer power. If we were to work instead with U8, for instance, which is not in this form, in fact we need p be a odd prime, and 8 is 2 to the power 3, then we would, if we multiply all the elements of U8, we should generate the element which is congruent to 1 mod n. So let's list U8, which is 1, 3, 5, 7. And note that 1 times 3 times 5 times 7 is equal to 105, which is in fact congruent to 1 mod 8. Okay. I think this is a immensely powerful tool, and you'll see how well it can be used to encrypt and decrypt. All right. So now I'm going to spend a few words of another preliminary that is necessary before diving into the algorithm itself, which is the idea of key exchange. I will be very vague because this topic is too broad and doesn't really pertain the explanation of the LSA. So please, when I'll talk about a share key or a secret key, just keep in mind that it can be any numerical object that is just known by two parties. All right, then we can start with the explanation of the algorithm itself. I'm going to call, as it's customary in the field of cryptography, I'm going to call the sender Alice, and I'm going to call the receiver Bob, so that I don't have to keep on saying the sender sent, the sender sending, the receiver receives. We give them these two names. Okay. Everything starts with K. I say it again, K is a secret number. The Alice and Bob Matt, they whisper in their ear K. Also, let me open a quick parenthesis. There are applications in which this the key exchange is not even necessary, and in fact is where the LSA obviously will be more useful, and we believe much more efficient the other algorithms existing. Okay, we have a number k, and assume that out of this number k can an integer part can be extrapolated. So we start with, since this is known by Alice and Bob, now that independently out of k they're gonna find an integer n such that we want n such that n is greater than k and n is in the form p to the t to p to the power t, where p is an odd prime and t is a positive integer. Not only k is the first integer, n is the first available integer that satisfies these two conditions. Let's make an example like before. If for any reason our k is 8, then the first number that is greater than k and is in this form is going to be 9. So out of 8 we're going to have that our n is going to be 9. Okay, so now what do? When they both agree on n, then they gonna independently create un. Remember that un is the group of all the integers less than n and coprime with n, equipped with multiplication modulo n. So we go, let's list them: a1, a2, a3, all the way to a sub phi of n. Okay, so note that n is known only, k is known only by Bob and Alice, so n, so the group un, no one knows that they're gonna both refer to this group, and they know exactly what elements they are in the group. So what do at this point? They all know un. At this point, they both they will both list the element of the group in ascending order. Obviously, you'll see after that is not the only condition. Like you can definitely list the elements in descending order. For some reason, in some cases, you'll see that is even better. But we'll see this after. But you'll see that it'll come natural to say why it just ascended, as long as they agree. So for the sake of the explanation, we'll list them in ascending order. So they're going to rewrite un in the form, let's change the name to the elements, we'll call them epsilon. We'll have epsilon sub 1, epsilon sub 2, epsilon sub 3, epsilon sub phi of n, and the condition we want them in ascending order, so epsilon sub j sub I is less than epsilon sub j whenever I is less than j, and again 1 less than or equal I and j less than or equal phi of n. Okay, so they have the group in ascending order. They both listed it. Now Alice starts the encryption. So she has assumed that she has obviously a secret message to send to Bob. Let's assume that this message is in a symbolic form, so numerical or like an alphanumerical. Allow me for the for the sake of the explanation to assume that she's sending some letters, and she's sending a word message. So what she's going to do is she's going to choose an element of the group to represent her plain text. To do this, there are many ways. The easiest now for this presentation is assume that to each element I can pair a letter, so that sub 1 will represent A, sub 2 will represent B, C, and so on. As long as I have enough elements of the English alphabet, and maybe including numbers, so we need a larger group that obviously unite. But you'll see that we don't need too much large of groups. The groups shouldn't be too large too, and this will make the algorithm very fast. Anyways, Alice will pick an element that represent her plain text. For instance, to be very clear, if she has to send the letter C, then if she has to send the letter C, then she will choose this element. So she will choose epsilon sub 3. So let me please list this again. Un equal sub 1, sub 2. Let's call epsilon sub h, epsilon sub h plus 1, all the way to epsilon sub phi of n. I did so because this will help me to explain. And assume that epsilon sub h is the plain text, or the representative of the plain text. So this is what Alice wants to send Bob. So what she does is she's going to perform epsilon sub 1 times epsilon sub 2 times epsilon sub 3 times all the way to epsilon sub h mod n. This is her ciphertext, and we call it C. Okay, so there are some instances where this is not that straightforward. So in the explanation, I'm gonna explain the most the simple way, and then I'll go back because I believe that this is the easiest way to understand the algorithm. Okay, so she's gonna send C to Bob. So Alice sends C to Bob. Alright. Then once Bob receives C, what he's gonna do? Now we have Bob doing C times epsilon sub phi of n. See? He receives C and starts multiplying C by all the elements in descending order. For this reason. So he multiplies C by epsilon sub phi of n, and he checks congruence to -1 mod n. If this is true, then he stops. If this is not true, then he's gonna perform C times epsilon sub phi of n times epsilon sub phi of n minus 1, and checks again, is this congruent to -1 mod n? And if it's not, he'll keep on multiplying. Sorry about the scrolling, I have a problem with scrolling the screen. All the way to C times C sub phi of n times D sub phi of n minus 1 all the way to epsilon sub h plus 1. Why to h to epsilon sub h plus 1? Because this is guaranteed be congruent to -1 mod n by Gauss's generalizations of Wilson's theorem. In fact, let me go back to the theorem for a second. All right. Remember, we choose n being this form. Obviously, we exclude the fact of n being 4 because it would be useless to work with U4 since U4 has only 2 elements. So unless Alice wants to send A or B or 2 numbers, that is really useless. So we want n to be in this form. We know that if we multiply all the elements of un, when n in this form, we generate the element which is congruent to -1 mod n. And in fact, what happened here is Alice multiplied all these numbers together and sent this chunk to Bob, who in turn started to multiply all this by this, and then since this was not congruent to -1 mod n, multiply this element, this element, this element, up to this element here. At this point, as you see, all the elements of the group have been multiplied. And so we must generate an element that is congruent to -1 mod n by what Gauss said. And since we believe him, then this is true. However, since UN is a group, and since the closure property of a group is guaranteed, then any elements, by multiplying elements together in any order, then we might generate the element that is congruent to -1 mod n. So we might generate n minus 1 multiple times, and not only when all the elements have been multiplied. So, and this might be unpredictable. So actually, I don't know. I don't know if it's unpredictable. So what Alice is going to do is before sending C straight to Bob, she's gonna perform. So we're actually going a little backward, and this is I showed you the most straightforward way, which will actually never works, or is very risky. There's a risk to create ambiguity on the plaintext. So in order to avoid this ambiguity, what Alice is going to do is, when she finds C, when she'll multiply all the elements up to, remember, C is equal to epsilon sub 1 times epsilon sub 2 times epsilon sub 3 times epsilon sub h mod n. Alright, when she finds C, she's going to check how Bob is going to decrypt, okay, and how many times Bob will encounter during his multiplications an element congruent to -1 mod n. So Alice herself going to perform C times epsilon sub phi of n, and record and checks this congruent to negative 1 mod n. Then c times epsilon sub phi of n minus 1 times epsilon sub phi of n. If this congruent to n minus 1, again, sorry again about that, all the way to c times epsilon phi of n, epsilon sub phi of n minus 1, epsilon sub h plus 2. She does it all the way to epsilon sub h plus 2 because she knows already that if she does it up to epsilon sub h plus 1, that would be congruent to negative 1 mod n, and records all the times that this congruence is true as sigma. So sigma is going to be the number of times that by doing this multiplication I'll generate a number that is congruent to negative 1 mod n before the have multiplied all the elements together. Okay, this is guaranteed by Gauss's generalization. All right, so this is how it works. And at this point, what Bob is going to do is, and Alice at this point will send to Bob a tuple that is our ciphertext is going to be in the form of C, which is the integer that has been generated by multiplying all the elements up to epsilon sub h, and the sigma. So Bob to Bob, that at this point knows I'm going to take C, multiply it by all the rest of the elements of the group in ascending order, sigma plus a number of times until I get to sigma plus 1 elements that are congruent to negative 1. Is really much easier to do than to explain, so I'll be giving an example after, but what Bob does at this point is doing C obviously times epsilon sub phi of n, he'll check the congruence to negative 1 mod n, and then C times epsilon sub phi of n times epsilon sub phi of n minus 1. Is this congruent to negative 1 mod n? All the way to C times epsilon sub phi of n times epsilon sub phi of n minus 1, all the way to epsilon sub h plus 1, which is going to be the same path. Obviously he's going to do the same as before. Here we'll not have to check anymore because this is obviously congruent to negative 1 mod n. And he's gonna stop when he'll find this congruence to negative 1 mod n. In performing this part of the algorithm, he'll find sigma times elements congruent to negative 1 modulo n. Okay, then let's give a nice example. All right, assume that the integer, I'm going to work with a manageable group now, obviously, like try to keep it contained, not even with a super small group, but something that I can do here by hand. So assume that the integer that Alice and Bob share know, then that it's secret, no one else's know, is 53. Equal 53. Then we said that Alice and Bob will look for the first integer available that is greater than 53, strictly greater than 53, and is in the form of a prime raised to the a positive integer, or twice not prime raised to a positive integer. So out of k, they got an n which is equal to 54. In fact, 54 is greater than 53, and 54 is equal to 2 times 3 cubed. All right. So we know by Gauss's generalization of Wilson's theorem that in U54, if I multiply all the elements together, I'll generate 53. So, and now the element that is congruent to negative 1 mod n. Alright, then Alice and Bob are going to list all the elements of U54 in ascending order. So 1, 5, 7, 11, 49, 52. Alright, this is our group. The elements are listed in ascending order. So let's say, let's assume that Alice wants to send the element 19, or maybe she wants to send, if we pair this with letters A, B, C, D, E, F, G, she wants to send the G. Or if we pair this with the numbers, we have, this is the first one, 1, 2, 3, 4, 5, 6, 7. Maybe she wants to communicate 7. This is up to the agreement that we stipulate before, to how to match the elements of the group to the plaintext. Anyways, she wants Bob to know that the element she chose is 19. So Alice does 1 times 5 times 7 times 11 times 13 times 17 times 19 mod 54, which is congruent to 17, and this is our C. Okay, so this is the first part of the plaintext, and then so we have let's remember, this is our C, and then remember she is going to check how many times Bob will encounter multiplying 17 by all the other elements. She will generate 53. So she does 17 times 53, which is the last element. Okay, and then the next one is going to be 49 times 53 mod 54, which is congruent to 30, which is 37. Congruent to 37. Then we're going to have 37 times the next on the list, 49 mod 54, which is congruent to 31. Okay, so these elements are now congruent to negative 1 mod n, so we can keep on multiplying. 31 times the next on the list, 31 times 47 mod 54, 31 times 47, which is indeed congruent to negative 1 with 53, which is congruent to negative 1. Okay, so this one will go on the list of sigmas. So up to this point, sigma is equal to 1. Okay, so then she's going to do negative 53 times next one on the row, on the line, 43. let's do this. 154 is congruent to 11, and then 11 times 41. Mod 54 is congruent to 19. Alright? All the way. She has to check up to 25. Okay? Nineteen times 37, the next on the line gonna be congruent to 1. 1 times 35, that's 35, and then we have 35 times 31. Sorry about that, I try to rush a little. It's going to 5, 35 times 31, yep, correct. And then 5 times 29 is congruent to 37. Okay, so she went through the process that Bob will go through, and she realized that there's another time that Bob will find congruence to -1 mod n, and it's only one time. So at this point Alice is ready to send the ciphertext to Bob, which is composed by C and sigma. So we'll have C equal 17 and 1. Again, when Bob receives that, he knows that he has to start multiplying 17 with all the elements of the group U54 in descending order as many times as finding sigma plus 1 elements congruent to -1 mod 54. So let me just copy this. Okay. All right. So what Bob does with this, he just received our the ciphertext, and is going to start the process. So he just knows that he has 17. So start 17 times 53. Right? It's congruent to 37 on 54. And then we have 37 times the next one in line, 49. Okay. Obviously mod 54. Sorry, I'm switching this, is easier this way. Is congruent to 7, 49, 30, 31, and then 31 times 47, 54, 31, 47, congruent to -1, congruent to obviously 53, just congruent to -1. Okay, he found one, so he knows, again, he knows this is gone. So he knows that the next on the line, the next time he's going to find the congruence to -1 mod n, he'll have multiply the whole group. All the elements of the group have been multiplied. So the next on the list is going to be the plaintext. Okay, so let's try it. So now we have 53, sorry, let me put this up. Then we have 53 times 43, we're here, times 43, it's going to go into 11. Then we have 11 times 41, here, 41, I'm going to 19. We have 19 times 37. I'm going to 1 times 35. I'm going to 35, obviously. Remember, we have this other 35 times 31. I'm going to 5. 5 times 29. 37 times 25, 7, and obviously now we have the 7 times 23 or 24. 7 times 23 is 161, yeah, which is congruent to -1 mod 54. Okay. At this point, it generates another element congruent to -1 mod 54. He knows that this is the one that Alice was poking at, so he knows that the next one after this in the descending order on the list, he's gonna be the plaintext. So 23, he knows that of the next one he'll have multiplied is 19. So 19, so Bob knows that 19 is the plaintext. And this is the algorithm works. Thank you for watching. We'll add more videos on how to find a large number of keys, how to use it in more practical way, and on applications. But thank you very much for watching.